Hi, my name is Berkay and here I am with another video. In this video, I am going to show you how to analyze an audio with using Spectrogram. And after that, we are going to design our own two-stage FIR bandpass filter. And then we are going to do a quality check on those filters. And we are going to see if they are working correctly. And after that, we are going to filter our audio. And that will be it. Now this video will be a little bit different uh, from other videos because I was just going to one take this video, so this video will more likely like a live stream, so there might little errors in this video and little mistakes, but I want you to see how to analyze an audio using a spectrogram and how to design your own filter from zero to end. So let's start. First, let's load our signal, and as you can see, my signal, this is my signal's sampling rate and it's 44,100, and I have two channel signal in here, as you can see. Now let's hear our audio. Now, you can hear somebody singing clearly in this audio, but also you can hear another birds singing, and you can also hear background noise. And we are going to filter out all those things, and we are just going to hear somebody singing. And if you are interested in birds, you can check this website to find more bird recordings. And so let's start. First, we're going to analyze our signal with using spectrogram. Now let's just specify our power and our frequency and our time vector, and not u. And let's use spectrogram function. I need to specify my signal, my hum windowing, and overlap, and I don't care about size of my Fourier transform and my sampling frequency. Okay, now let's cross it. Now I need an image. First, I am going to specify time, after that frequency, and after that power spectrum of my signal. Then I'm just going to change axis. And oh, I forgot, because of my signal has two channels, I need to specify a channel. So I am going to specify my second channel, and after that let's add an accent and label, and it would be time, and it will be second. Your variable will be break, and it will be in hertz. Okay, now and I need to specify color maps at hot. Okay, now let's see. Okay, now you can see a little sparks in here. This means all the energy, most of the energy is in here, but there must be something below this spike and something's up, but we can see it. I need to specify color limit of this image, so let's use set and let's specify our color limit. It will be from 0 from level 0 to 1 and multiplied by 2, and I am going to specify a yaw limit, so it will be from 0 to 10,000 is okay, I believe. Okay, now let's see. Alright, this is such a good spectrogram. Now as you can see, there is something happening between these frequencies at these seconds and these seconds and these seconds, and there's something also happening in here, and I believe this is just noise. And let's see, let's hear our recording again. Now let's do it again. Now you you can see that somebody's singing frequency is between these frequencies, and this this is all somebody's singing, and this is other birds singing, and this is just noise. Now we are going to make a bandpass filter between these frequencies to filter out every other sound in this recording. Now I need to know exactly which frequencies I am going to use, so let's do it again. Oh, okay, now it seems like I need to use cutoff low frequency as 4900 and cutoff high frequency as 6500. Okay, now I know my cutoff frequencies, and let's specify some parameters. First, I'm going to specify my cutoff low frequency, and it will be equal to 4900, and this will be for my high pass filter. You can see, and let's specify cutoff high frequency, and it will be equal to 6500, and this will be raw pass filters frequency. Okay, now I need to specify my Nyquist frequency, and it will be equal to it will always equal to half of my sampling frequency. Now let's specify our order of my filters. So first I am going to specify my high pass filters order, so order high will be equal to 10 multiplied by round sampling frequency divided by cutoff low frequency. Okay, and this will be my order of high pass filter, and let's specify order of low pass filter, and again 10 multiplied by, so round, sampling frequency divided by cutoff high frequency, and this is the order of low pass filter. Now I specified my cutoff low frequency, cutoff high frequency, order, and Nyquist frequency. Now I can create my filters. Now let's do this. Okay, now first I need to create my high pass filters canal length. So let's create our canals. Equal to, I am going to use FIR1 function. First I need to specify order of my filter. I'm going to use order high, and after that cutoff low frequency divided by Nyquist frequency, and after that I am specifying my type of my filter, and this will be a high pass filter. And let's create a low pass filter. Again, FIR1 function. First I need to specify my order, and after that cutoff high frequency divided by Nyquist frequency and a low pass filter. So this is canal of my low pass filter, and this is the canal of my high pass filter. Now I have created my filters. Now I need to check them. So how I am going to check them? First I need to look at the time domain response and frequency domain response, and for this frequency domain response I need to calculate power spectral of my canals, both of my canals. So I am going to calculate power spectral of those filters. So let's start. In here, quality. Now I'm going to first I'm going to calculate my high pass filter scanners, and I'm adding power spectral. After that I'm going to calculate power spectral of my high pass filter scanner. Now let's calculate our low pass filters power spectral, and it's in here. Okay, now I have calculated both of them's power spectrum. Now I need to create a time vector for each of them, because as you can see in here, they have very different length, so I need to specify different time vectors for them. So time vectors, let's add this power here, and power spectrum of low pass filter. Let's create a time vector and line space. It will start from 0 and increase frequency, and after that roar length of canal high divided length of canal high divided by 2 and plus 1. And let's create low pass filters, power spectrum time vector, line space 0, increase frequency, and again floor length of canal low divided by 2 and plus 1. Okay, now I have created my time vector and I have created power spectrum of my canals. Now I am ready to plot it and compare it, and let's see if they are working correctly. Now figure, let's do a subplot to 1. Let's plot time domain response of my high pass filter. So it is canal high, and we need a titer for it, and its titer will be response of high pass filter. Okay, now again subplot. Now we are going to plot our frequency response of high pass filter. So let's plot, let's do it, and after that high 1 to do length now we need a titer for it, and you can see domain response of high pass filter. Okay, now let's do it again for the low pass filter, and I am just going to do that. Let's copy, let's change this. This will be low, and this will be low too. This will be low again, and a low pass filter, and this will be a low pass filter too. Now let's see, finger cross. Oh, okay, this is nice. You can see the time domain response of my high pass filter and time domain response of my low pass filter in here, and this is the frequency domain response of my low pass filter. As you can see, it is hard to see the frequency, so I am going to limit x-axis. So set is x from 0 to 8000. And I believe I am going to make line width 2, and I will going to same one in here. Let's specify line width as 2, and again, now you can see that this is the time domain response of my high pass filter scan, and this is the frequency domain response of my low pass filter. As you can see, it is 0 until 6500, and my high pass filter will not pass anything below 400 and 500, 4500 frequency, and it will going to let it pass everything greater than 4500, and my low pass filter will not permit anything to pass after 6500 frequency. But I didn't like my high pass filters attenuation period, so I am going to do something in here. I'm going to double the order of my high pass filter. Let's do it, and let's do it in here. Okay, now this has a better attenuation period, and I'm also going to increase my low pass filters orders because I didn't like it. Again, okay, this one is better, and this one is better, much more better, and I just need to filter out my signal. So you always need to control your high pass filters scanner and your filter scanner, because you might made a mistake during a process, and you just need to check them. If you don't check them, you will be a sloppy signal processor. So always check your filters. Now let's filter out our signal. And filter out, I'm going to use FIR function. This function comes with a signal processing toolbox. And first I am going to specify my filter canner. First my canner, and after that one, and my signal. And this is what I am doing in here is I am high pass filtering my signal in here. Now I am going to use low pass filter, so let's specify filter signal. Again, I am going to use FIR function. And after that, I am going to use low pass scanner, and after that I am going to use my filter out, not my signal. This is two-stage bandpass filter, and let's hear our filter, shall we? Filter signal and FS. Now you can only hear somebody singing. Now I want you to see spectrogram of this filter signal too. So I am going to just copy paste this in here, and I'm going to just do this, and I'm going to do this in here too, and let's delete this. And this is the spectrogram and the recording of my filter signal. And this is it. In this video you learned how to use spectrogram to analyze an audio signal, and after that you learn how to determine your cutoff low and high frequency. Then you learned how to make your own canals, filter canals, and how to filter out your signal. And this is it. Thank you for listening to me.